Good day Philippines and good day world! I'm Glyra Valencia and I'm going to show you some lessons in biochemistry in a fun way. But first, what is biochemistry? Now, here are the answers of some people from different fields.
Hello, I'm Mean Principe, a graduate student of Humanities and Social Sciences and taking a Bachelor of Secondary Education major in English. And biochemistry for me is it is the branch of science that is concerned with the chemical processes with regards to the living things or organism.
Good afternoon, I'm Shane Marjolino and I'm currently studying my master's degree in UST. So my idea about biochemistry is that since I'm a food science student, my idea is that biochemistry is the utilization of the body of the macromolecules and the micromolecules for human health. So that's it. I am Lorraine Bainto, Assistant Professor at the Institute of Food Science and Technology, University of the Philippines, Los Baños. So biochemistry, in a simple definition, is a branch of science that deals with different chemical reactions occurring in living systems. So for us as faculty members, teaching food chemistry, it is very important to have a strong background in food biochem. Because since food technology is an applied science, we need a strong background so that we can explain the principles behind each application in food.
Here's the other definition of biochemistry. Biochemistry is the study of chemical processes in living organisms which gives rise to the complexity of life. It is also called as biological chemistry. But why am I tackling biochemistry all of a sudden? Well, just to share guys, I just really got inspired with our quiz and exam in biochemistry, which I don't really know if I can survive there or not. So maybe this will also serve as a notice to my parents. Nay, Tay, I offer you this.
I did my best, but my best wasn't good enough.
I'm sorry if my voice sounds like that. I'm not really feeling well, but no worries, body temperature goes back to normal through homeostasis.
What?
Homeostasis. It refers to the ability of an organism to maintain stability in spite of changes. Now let us define life scientifically. Life is defined as a distinctive characteristic of a living organism that is distinguished by their capacity to grow, metabolize, respond, adapt, and reproduce. Here, we are going to focus about growth. As I promised that this learning will going to be a fun way, I'm going to show you some pictures of Korean heartthrob Lee Jong-suk while he is growing up. Vlogger, and to make it more reality, I'm also going to show you my growing up pictures, even I'm shy. Just like histidine, lysine, cysteine, phenylalanine, alanine, glycine, threonine, cytosine, valine, proline, arginine, glutamine.
Professor Dave here. Let's talk about amino acids.
He knows a lot about the science stuff. Professor Dave explains.
Your body is full of large molecules called biomolecules. And the first thing we have to do to understand biochemistry is to learn about the different kinds of biomolecules. There are a few different classes, like proteins, carbohydrates, lipids, and nucleic acids. And most of them are polymers that are comprised of repeating units called monomers. Mono means one, poly means many, so a polymer is formed when many monomers link together. Each polymer has its own type of monomer, so we need to know about these different kinds of monomeric units and the ways they combine to form the large molecules that do all the complex things in your body. The first type of monomer we will learn about is the amino acid. Amino acids look like this. They all have an amino group on one end and a carboxyl group on the other end. The carbon in between those functional groups, which we call the alpha carbon, will bear a side chain, sometimes referred to as an R group. This is a group that varies depending on which amino acid we are looking at. If the R group is just a hydrogen atom, we call this amino acid glycine. If it's a methyl group, we call this alanine. There are about 20 of them, and they have a wide variety of R groups that can be put into different categories. Some of them will be hydrophobic, like leucine. These are the ones with R groups that are alkyl substituents. Some of them have R groups that are aromatic, like phenylalanine. Some have R groups that are basic, like lysine, because of the lone pair of electrons on the nitrogen atom. Some have R groups that are acidic, like aspartic acid, because of the carboxyl group. Some have R groups that can act as nucleophiles, like serine, because of the hydroxyl group. Every amino acid has its own unique structure and reactivity, and it's the variation in these R groups that determines the characteristics of the molecule that forms when a bunch of these amino acids join together. Some of these amino acids humans can't make on their own, so we have to eat them in our diet. They are called essential amino acids. Others we are able to make inside our bodies, so those are called non-essential amino acids, meaning it's not essential that we eat them. So amino acids are monomers, and monomers are the units that join together to form a polymer. How exactly then do amino acids polymerize? Before we learn about that, let's first understand that inside the body, instead of the one structure we've been looking at, there are actually equilibria between different forms of the amino acid. The amino group can be protonated, since it is slightly basic, and the carboxyl group can be deprotonated, since it is slightly acidic. And there are equilibria between the cationic form, the zwitterionic form, and the anionic form. We know what cations and anions are. They're positively charged and negatively charged species. And a zwitterion is a molecule that has both a positive and negative charge. The form that an amino acid will take depends on the pH of its environment. A more acidic solution will favor the cationic form, since basic groups will pick up protons from the hydronium in solution. And a more basic solution will favor the anionic form, since acidic groups will readily deprotonate in the presence of hydroxide. Inside the body, the pH is regulated very precisely, and in most areas it's fairly close to neutral pH, so the zwitterionic form is typically dominant. The side chains can also have different states of protonation or deprotonation depending on the pH, such as lysine, where the R group can have NH2 or NH3+. For now, let's just look at something simple like alanine. At physiological pH, it will take this form. What sort of chemistry can this do? It might not be obvious just looking at it, but with the help of other molecules in the body, these can polymerize to form proteins. So let's move ahead and learn all about proteins.
Anne-Marie Dando Principe. I graduate with love. Go na!
Tayo ngayon. Bye! We're on the way to interview someone. Yo! Ito yung aming camera woman na aka driver. Siya po ay si Miss Jasmine Bayan, future RN ng
A dot isn't the best way to try to sum up how electrons come and go. They are the states of a matter field that follows an equation that Dirac wrote. The Schrodinger part of the whole equation will just lead in sub C when it expands. Now get that cool thumb and add it in with the proton and watch them start to dance. It's hydrogen, it's like, oh proton, I feel your tug. Central potential, dip down, pulling on me. But I'm not falling in deep. Know that would break uncertainty. Say, oh, electrons move too much. Slow down your pace and put that orbit on me. Come on now, follow my lead. Come on now, follow my lead. Orbitals take the shape they do, the stable states of the quantum rules. And when one approaches two, they combine in the bonding. Thus hydrogen as a rule is found in nature as H2. Energy configuring a molecule, diatomically bonding. High, low, high, low, high, low, high. Diatomically bonding. High, low, high, low, high, low, high. Diatomically bonding. High, low, high, low, high, low, high. Diatomically bonding. Energy configuring a molecule. When orbitals take the shape they do. One half spin will give a left on a twin. One up, one down in the ground state. With S&P and quadruple degeneracy, the second shell can be filled up with 8. The higher angular power spread all the beautiful flowers and middle families that come into play. Well, here's a carbon with 6C. This ain't nothing tricksy, but we're gonna make some methane today. With hydrogen, it's like, oh atoms, I feel your tug. Got my electrons plugged out, pulling on me. Come on now, settle around me. I'll hybridize to sp3. Say, oh, carbon, here's our touch. Spread out 109.47 degrees. Come on now, follow our lead. Come on now, follow our lead. Molecules take the shape they do, combining states of the quantum rules. Like when a shell goes sp2 for sigma pi double bonding. And as widely as their purview, they spread out in the molecule. Like a benzene in a ring, they hold it true, aromatically bonding. High, low, high, low, high, low, high. Aromatically bonding. High, low, high, low, high, low, high. Aromatically bonding. High, low, high, low, high, low, high. Aromatically bonding. Look at benzene in a ring, they hold it true. When orbitals take the shape they do. Come bond with me, baby, come bond. 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 Polymers take the shape they do, combining base level residues like RNAs, ACGU. They're hydrogen bonding. Peptides make a chain and group in beta plate sheets and corkscrews. With the secondary links they fold and move. best to do. The molecules take the shape of you.